What happened in the last lecture is we looked at replicated secret sharing and Shamir sharing, which were Q2, and we looked what it meant for those secret sharing schemes to be multiplicative. Now what we're going to use now in the next few minutes is we're going to explore how the multiplicative property allows us to actually do multiplication. Recall that the scheme is multiplicative if we can represent as the product of the things being shared as a linear combination of the Sure product. So that's what multiplicative meant. So given we've got a multiplicative secret sharing scheme, we can actually define a multiplication protocol, and probably the most famous of this is one that was, we call it Maurer's multiplication protocol, but it was probably known before that, but Maurer was the first to kind of like formally express it. So what we have is, remember we can compute, we've got a linear secret sharing scheme, so we can compute linear functions for free. So what do? Well, step one is we form the Sure product of the parties' shares, fine. Now remember, we know that the product is a linear combination of the things in that Sure product. So we express the product as a sum of the local Sure products. We might have to take a subset of them. And then each party reshares its bit of the local sum, and then they finally recombine them together. And so the point is that steps 3 and 4 are effectively evaluation of a linear function, which we can do for free because it's a linear secret sharing scheme. And the product can be formed and it gives us what we want because we've got a multiplicative linear secret sharing scheme. The only downside is it requires interaction. So we need to interact, we need to send messages when we want to perform a non-linear operation such as multiply. So how does this work in practice? How does this kind of like 4-step process work? We'll explain that with Shamir and then a replicated so you get it, you can really understand it. Okay, so let's go back to multiplication by Shamir, the traditional way it's expressed. Okay, so what we have is we want to share two secrets, S and S dashed. We sharing them via polynomial f and f dashed, both of degree t. And so each of the parties has the evaluation of the polynomial at their index I. The parties first compute the Sure product. That's the first step they do. So what is the Sure product in Shamir sharing? Well, they've both got a share of one secret and they've got to share another secret. They just multiply them together to get a value ti. Now this ti, as we saw in the last episode, is the evaluation of the product polynomial. So this is a polynomial of degree 2t. But we know, because it's a polynomial of degree 2t, that the Lagrange interpolation, we can express the product as a linear combination of these values ti. Okay, so what they do is that each party sets ui to be lambda I times ti. Lambda I is public. So what we actually have is that the product s times s dashed is actually a full threshold sharing of a value u1 known by party 1 and a value un known by party n. So this is what we really get out of the Shamir analysis. Okay. So we now actually create shares of the ui. So each party, party 1's got u1, he creates a sharing of u1. Party 2 creates a sharing of u2, and so on. So what does that actually mean? Well, okay, so each party generates a sharing. So this is in Shamir. So each party generates a polynomial gi of degree t such that the constant coefficient is equal to ui. And then it's going to send to each of the other parties the share value gi evaluated at j. And we're going to call this sharing of ui, we'll call it angle brackets ui. But we then have, because we can compute linear functions for free, in particular sums for free, that the sharing of the product in Shamir is basically the sum of these sharings here, because the product was the sharing here. So once we've done the sharing, we have it. So that's basically the multiplication protocol for Shamir. Recap, we multiply the products here in the Sure product, we express it as a full threshold sharing, we take each term in the full threshold sharing and reshare it, and then we just add all those sharings up that we just computed. How does this work for replicated? Okay, so for replicated, recall that let's look at the 3-1 replicated scheme. So we have sharings K1, K2, K3 of the value S, K1 dash, K2 dash, K3 dash of the value S dashed, and the parties hold these values as normal. As we saw last time, we can express the product of S times S dashed as a full threshold sharing of U1, U2, and U3, where U1 can be computed by party 1, U2 by party 2, and U3 by party 3. So this is, again, it's a full threshold sharing. But we don't want a full threshold sharing. We want a sharing in the underlying secret sharing scheme, this replicated sharing. So what we do is we simply, party 1 does a threshold sharing, their replicated sharing of U1, party 2 does a replicated sharing of U2, party 3 does a replicated sharing of U3. So that's how they do it. So party 1 who wants to share U1 is going to write U1 as V1, V2, and V3. He's going to send V1 and V3 to party 2. He's going to send V1 and V2 to party 3. He's going to retain V2, 3, 3. And from that, they can, all of them, when each one has done, each party 1, party 2, and party 3 have done that, they can compute the sum and therefore the product as normal. So again, we have express the product as a full threshold sharing, take the value, share that in terms of the underlying secret sharing scheme, and then just add all the shares up. So it's very similar. So this gives us this passively secure multiplication problem. The problem is in step 3 is that an adversary could lie. So it could produce an invalid sharing, or it could share the wrong value. So we might not actually get the right multiplication. So later on, we're going to have to test whether we've actually got valid sharings of random products, which we'll do later in a process we call sacrificing. So how do we do this how do we use this multiplication protocol to do multiplication triples? It's very simple. We take A and B from a PRSS, which generates a random value of A, random value of B. We execute Maurer's multiplication protocol, and this gives us the random sharing of the product C. So, but we just, at this point, we don't know whether, if we have malicious adversaries, we don't know whether C is valid or not. Okay, so the point is the active adversary can lie when he does the resharing. So we might have that C is not equal to AB, but C is a valid sharing, or we might have that C is itself not a valid sharing. But we're going to do, as I said, we'll deal with this later in the sacrificing step. If we wanted to produce square pairs, which are sharings of A and A squared, that's very simple. We just generate A again as PRSS. We then do the multiplication protocol with A and A. This gives us A squared, and we do it the same. Shared bits is slightly more difficult, so let's kind of look at this in more detail. So we're going to use a trick here, which is going to come up quite a lot. So what we do is we take a random sharing of A used via the PRSS, and then we're going to square it just like we did in the previous algorithm. So we are going to obtain a sharing of S using what was on the previous slide. But now what we do is we open S. So everybody learns the value of A squared. Okay. Now we're going to reject this if S is equal to 0, because if S is equal to 0, then actually A is 0, and so there's nothing here. Now, remember we're working over a finite field of odd characteristic, okay? So what we can now do is we can take square roots. So we take square roots of the value S. So what's that equal to? Well, S was equal to A squared. So if we take a square root and we do it in a kind of deterministic manner so that we know, so for example, we always take the square root which has the least significant bit equal to 1 or something like that, then everybody obtains the same square root, but we don't know whether that square root is equal to A or whether it's equal to minus A, okay, because we don't know what the original value of A is. So now what happens is if we divide the secret shared value A by this square root of S, then actually the value we get out is minus 1 or 1, but because we don't know A, we don't know whether it's minus 1 or 1, because we don't know whether square root of S is equal to minus A or A. But notice this operation is a linear operation. It's taken a secret shared value and it's dividing it by a known constant. Okay, so now we've got a value that's in minus 1 or 1. So we can now turn it into a bit by just adding 1 to it and dividing by 2, which is again a linear operation. So here we have some communication in step 2 to do Maurer's multiplication to get the square, and then we have some communication to open this squared value, but the rest is all just linear operations. It's very simple. So that's how we do shared bits. Input data is rather trivial, is that party I just generates a random value and then distributes shares to all other players. If they lie, if they distribute something which is invalid, it's an invalid sharing, and this is going to be detected later. Or if they lie and they actually distribute something valid which isn't equal to R, then actually the only person who's going to be affected by this is them, because they're not going to be able to enter the right value in the protocol, or they're going to get the right answer out. So this is not so much a problem. Okay. So input data is relatively straightforward. So that's it for now. We've now worked out how to do the pre-processing, except for the sacrifices step, which is not going to be that hard, for Q2 access structures. Next time what we're going to do is do the same kind of stuff, but for full threshold access structures. And full thresholds is a little bit more complicated because full threshold access structures are by definition not multiplicative. So we can't use this trick of having a multiplicative secret sharing scheme. We can't use this trick of the Maurer multiplication protocol. So we've got to be some other way that we can get products out of our secret sharing scheme in the pre-processing phase. So that's what we're going to cover next time. Hope you've enjoyed this, and see you next time.